Let us start this lecture with a thought process from Henry Ford. When I cannot handle events, I let them handle themselves. So, if you look at in the last lecture, we basically discussed about the diffusion flame, various kinds of diffusion flame. Then we initiated discussion on the jet diffusion flame. In the process, we looked at the various structures of the jet diffusion flame. And today what we will be doing, we will be basically finding out an expression for flame height using the phenomenological analysis. So, we are making this following assumption for this, that we are saying this is the flow is laminar steady inviscid flow, right, and that is the things we are talking about. And then the flame is diffusion control. That means the flame will be basically governed by the how fast the fuel is diffused into the quiescent atmosphere in the oxidizer, and that will govern not the reaction rate. And the Vz remains constant along the HF, which is not true. That means the axial velocity remains constant along the flame height, which will not be true, but however we are doing it for the simplicity reason. And buoyancy effect is neglected, because if you look at this is the quiescent atmosphere, and the some amount of fuel is being burned and lot of amount of heat being released. As a result, there will be buoyancy effect apart from the momentum which will be coming due to the jet. That is being neglected. And constant thermophysical properties, which we will be using most of our analysis, not only for this, otherwise we cannot really handle. Keep in mind that in combustion process generally the thermophysical properties do change with temperature, because temperature change in case of a combustion is quite high. You cannot neglect it, but we are doing for a simplicity reason. So, we will have to now define a flame height, right. The flame height can be defined as a point along the axis, right, on which interdiffusion of fuel and oxidizer reach on the flame surface for the first time. Of course, this definition is very limited. Let us say this is the I have taken a little different kind of thing configuration, and if you look at this definition, what it says, if there is a only fuel jet and you will get a flame, this is known as over ventilated flame, right, and this flame is basically what is saying, it is the height HF from here this distance to this distance, right, that is known as flame height. And what is saying, it is because if this is the fuel will be diffusing into that fuel and oxidizer will be coming that, and it is not at the center line, number one, and then the flame will take place, it will goes on at the center line, it will be reach so that the fuel and oxidizer will be at this height will be coming contact on this axis, right, and that is known as flame height. And this is a valid statement only for the over ventilated flame. If there is a under ventilated flame, this is the flame, you know, this flame is the under ventilated flame, right, where the air is very less amount, right, and then fuel is much higher, so that flame will be getting into that. But that is very rarely you will get unless you control. Natural flame will be always over ventilated flame. Are you getting? Natural jet diffusion flame. So, therefore, we will be using this definition HF, and the what we need to know is basically the time required for oxidizer to reach the axis of the jet. If you look at, this is my Z axis, this is my R axis, the oxidizer is coming over here, right, oxidizer, and fuel is coming over this due to diffusion, and it will be coming such that it will be reaching the axis of the jet, because the time, what is the time required, that we will have to look at, and this is coming due to what? Due to only the diffusion, only the diffusion. That means the momentum we are not considering, right? It's only, it is as if it is diffusing and then it is coming. So then we can say that this time whatever is required is nothing but your Hf divided by Vj. That is a one way of looking at, because it is having certain momentum, right, and which is having a velocity Vz at this point. This we are saying it is a uniform velocity, and that is Vz, right. And the, if I already assume that Vz is not changing along the z direction, along the flame. So therefore we can say that time required for the fuel to reach this height will be basically governed by the Vz. That means Hf divided by Vz is nothing but your T, time required, and that is the fuel to reach. But the oxidizer to reach will be by the diffusion, right. So by this Einstein diffusion equation we can have this R dash square is equal to 2 d1 to T. T is the again time required for that is and d12 is the diffusivity. This is the molecular diffusivity, right. And R dash is basically average, and this is average square displacement due to molecular diffusion. And I have already told you this is basically diffusive between fuel and oxidizer, right. 1 2 one can say fuel. So then I can write down, if I will just use, maybe this is equation 1 and this is equation 2. If I combine this together, what I can write down is Hf is nothing but your T into Vz, and T is nothing but your R square divided by 2 d1, and this R, the distance which is covered, if you look at, is basically this is your 2r, right. So that means from here to this distance is nothing but your r. So this r dash square is nothing but your capital R square, right, in this case. So therefore you will get Hf is equal to Vz R square by 2 d12. And if you look at that, I can say that this Hf is basically depends on what? It depends on the Vz. That means if Vz is higher, then flame height will be higher, and it will be dependent also the diameter. If diameter is more, right, or the radius or the diameter, like it will be also dependent on that, and the diffusivity is higher, the Hf will be smaller, right. If it is a lower, then flame length will be lower. So that you can think of, but let me look at it some other aspect of that. I can write down that Vz pi R square, right, I can write down divided by 2 d12 by pi. I can this is this portion, this is nothing but your volumetric flow rate. Vz is the velocity into area, that will give volumetric flow rate by 2 d12 pi, right, and this is basically volumetric flow rate. And if I write down this one is basically in terms of density, like you can say mass flow rate, I can say write down Hf is basically, I can say density of the fuel. I can say this one because this is the fuel flow rate, right, F into V dot divided by 2 pi rho D12, and this is nothing but your mass flow rate of fuel divided by 2 pi rho F D12. What is saying is that basically it is a independent of the diameter, rather the HF is a function of, it is a function of flow rate and it is independent of burner diameter per particular volumetric flow rate or the mass flow rate, right. And keep in mind that if I will take LE is equal to 1, that means alpha is equal to D, K by rho Cp is equal to D. So, I can write down basically K by Cp is equal to rho D. In place of this I can write down F by 2 pi K. I can say this is basically Kg, I can write down Kg gas by Cp, right. So, this you can also see that these are the properties which is basically do not change much. This Kg, this Kg by Cp won't change much with at the various temperature kind of things, won't change much. So, therefore, HF is basically proportional to the flow rate of the fuel. And keep in mind that we are not talking about the coaxial jet, we are talking about a single jet in this case, right. And the HF is as I told, for a fixed value of the mass flow rate, and HF is independent of the pressure, right. Okay. Because if I say this thing, because Kg and Cp won't be depending much on with pressure, right, because whereas the diffusivity is changing. So, therefore, you will find HF is not really very much depending too much on the pressure, flame length. So, let us look at how this will be having. This is the HF, this is from the experimental data, and you can see that I mean Reynolds number it is being put because of fact that you can see this Re is equal to rho Vz d by mu. D in this case is 2R, diameter of tube, and in this case this is basically fuel and this is fuel. Are you getting? This is the basically I can say fuel number of REF. What you can see as HF is basically increases with increase in Reynolds number, right, that we have already seen. That means HF we have already seen, it is basically depends on flow rate, that is HF is equal to Vz by R square to D12. So, HF by the goes by the Vz. So, it is increasing, right, and that is true for of course for laminar flame height or the laminar regime, it is true, but in the transition regime what is happening here, you can observe that the flame length is basically will be start decreasing, right. But however, this portion, this line is indicating is basically the onset of turbulence. Like if I draw here a which is not there, but if I draw a flame length here something like this, then what happen? This region is turbulent or a little bit transition means in a combination of laminar turbulent kind of or onset of turbulent, right. And here then what is happening, the flame length is remaining almost constant with the increased laminar, particularly for beyond this transition regime, right. Beyond this transition regime, it is remaining almost constant. But however, there will be also the envelope breaking point. That breaking point means where this portion, the flame will be turbulent in nature, right. There will be the flame brush will be coming, as I showed you in the premix flame, it will be randomly moving the flame surfaces, right, and that will be coming here. As you increase this Reynolds number, it is goes on decreasing this point, like for example, it started doing here only in the tips, right, but in the transition, but as it is goes, then what will happen, it will be goes on decreasing, which I have not shown. Another flame maybe here is very less, and it will be goes on changing, and it is remaining constant almost, because only the smaller portion nearby the jet inlet of the orifice of the jet, right, that there will be laminar, rest of the thing will be turbulent. So, this increase in flame height is observed until the turbulent mixing occurs, and this situation occurs at the flame tip, because this will start, the turbulent will be start occurring to dominate play a role, particularly in flame tip, moves downward as the velocity increases, that is moving downwards, right. And the position of transition from laminar turbulent is called the break points, right, where the laminar, because this is laminar, right, laminar, and these are the turbulent, right, and that position, like this position, this is the one position, this is the point, these are the break point, and break point remain constant beyond certain velocity or beyond certain Reynolds number, right, that is basically Reynolds number, right, kind of things. So, and transition Reynolds number is different for different fuels, that you should keep in mind, it is not same for all. Like your pipe flow, if you look at pipe flow, generally turbulent means, or the, that is Reynolds number will be what? What will be Reynolds number? 2200, right. But whereas in this case, the transition, this thing will be changing, right. So, if you look at this fuel air, if you look at transition Reynolds number for acetylene is basically 9500, and propane it is 9500, and whereas the coal gas 3500. Basically, if you look at coal gas, sometimes it is known as the town gas. Earlier days people were using, like using the coal, convert the solid coal into gas and then using in the town, particularly in England and other places, not in India. 3500. Carbon monoxide is 4800, hydrogen is 2000, it is a near to a pipe flow. So, this is the kind of things what it would be, I think. And keep in mind this, this fully developed turbulent flame is basically very noisy and also less sooty as compared to the laminar flames. Laminar flames are more sooty. But if you look at, let us look at little analysis and to show that whether this you can capture this phenomena of the flame height is remaining constant. So, if you look at the HF, right, is we have already seen that HF is basically Vz r square by diffusivity, and the diffusivity D12, like if you it can be used replace, because we have seen that HF in case of laminar flame we have seen is proportional to Vz, right, r square by 2 diffusivity, right, D12. This is case of laminar, right, laminar flame. But we will be using similar thing and then trying to replace this diffusivity is replaced by nu T. Nu T is the turbulent flow, right. Nu T means it is basically eddy diffusivity, and this is known as the eddy diffusivity, right. Basically eddy diffusivity, and this eddy diffusivity we know is basically is equal to length scale, like integral length scale, and V dash RMS, right, and which is proportional to, you can say that this length scale will be proportional to what? R, right. I can say that L is proportional to R, right, and V RMS is proportional to V Z average, right. Now, if you look at, I can write down this as basically that means is V T is proportional to R and V Z. So, H F I can write down for turbulent flow, H F I can write down as V Z R square by nu T is equal to, I can say this is constant, right, is equal to this is by R V Z, and this is, I can say this is a constant C T and V Z by R square, right. So, this will cancel it out, I can say this is average, this is cancel it out, and you can find out that this is nothing but R. That means H F, I can write down H F is equal to C T by R for turbulent flow, right, for turbulent flow. That means H F is not really depending on the velocity, it is because if the diameter is remaining constant for the experiment, you can see that H F is remaining constant, that means it is not dependent on the Reynolds number. What I am trying to say, these are the experimental data, right, these are all experimental data, right, and by using a very simple phenomenological analysis, you can get you can explain this variation using very simple phenomenological analysis. That is the thing you must appreciate. Okay, fine.
Then what is CT?
CT is a constant, right, because this is I am taking the proportional, right. So, naturally you will have to take a constant. CT is basically a constant. It can be any constant which will be from, you want to match the experimental value and put some constant, then try to match, that way. What I am trying to say that H F is independent of Reynolds number, that is the point I am writing. H F is independent of Reynolds number, that is the point what I am trying to say. So, let us look at like what are the jet diffusion flame, what are the things we can see, like if it is the flame here which is a turbulent, of course, jet diffusion flame, this is turbulent, this is the V jet velocity, I can say V jet which is increasing, right, V jet means at inlet, So, you will find a flame, and when you increase this flame, what will happen? Flame is lifted, this is the lifted flame, and this height is known as HL, lifted height, right. This is lifted HL, lifted height, flame height, and this is the flame height. Okay. As you are increasing, this may oscillate, go up, and then the blue color regions are increasing, and when you go beyond certain velocity, what will happen? Flame will be very, very small, it will go up, and then after that blowout will occur. Okay. That means this portion will be reduced and some kind of thing, it is I have not shown, we have conducted some experiment earlier. So, that is the things what I can say. Now, if you put this HF by D and put this data in terms of Froude number is basically the ratio of initial jet momentum to buoyancy forces, and this is Froude number, which is non-dimensional number. You can see these are the experimental data is being plotted, and which is varying, HF is varying with the Froude number, and after that it is remaining constant, and this portion where it is remaining constant is known as momentum dominated. That means here it is not affected by the buoyancy, and this will occur only when the V is very high, right, and or rather the Froude number will be very high and V will be very high and D will be small, right, kind of things, that where momentum dominated will be flame will be saying that flame height won't be changing much even though you are increasing the Froude number or the velocity, right. So, with this we will stop over, and in the next lecture we will be discussing about basically how to analyze the jet diffusion flame in a little more rigorous way. Okay, fine. Thank you.